So hi everyone, I'm Hongbo. I'm a PhD student at the Cornell University, and I'm going to talk about what makes the EVM slow. So currently there are almost 30 million blocks, and it will reach 30 million blocks next week. And there are more than 1 billion transactions on the Ethereum blockchain. While new transactions are being generated about 15 transactions per second. So on the Ethereum, it takes more than 1 week for a high-end personal computer with a very fast SSD to process the existing blocks and catch up with the most recent blocks for running a full load without a snapshot. Ethereum is rolling out its version 2.0, which hopefully will be able to process more transactions per second. And here comes the question, will the EVM become the bottleneck of the Ethereum blockchain? And it is not only about Ethereum itself. The EVM model has become the standard platform for smart contracts. Many other blockchain systems, including the Avalanche and the Binance Smart Chain, have adopted the EVM for executing smart contracts on their own system. Probably none of them have saturated the EVM yet, but we are still wondering what is the theoretical throughput of the current EVM design. And therefore, we started this benchmark study for the EVM based on the real data from the Ethereum blockchain. And our goal is to identify the past workload pattern for the Ethereum and the bottleneck of the current EVM. So we set up our benchmark platform as close as a high-end consumer level personal computer that people can get for home. It has a Zhang CPU, which is similar to the 8700K, and we use the default Go Ethereum memory configuration, and we use the fast Samsung M2 SSD for storage. Before we go to the benchmark result, let's first look at how the Ethereum clients process transactions. Upon receiving a block, it executes transactions one by one. If the transaction is a smart contract call, during the execution, all the changes are temporarily held in a in-memory map. And after finish executing the transaction, it updates the contract storage tree by generating the new tree nodes. And after all transactions are executed, it updates the global state tree. And then write back all the new blocks and the state to the persistent database. Therefore, there are two paths for the EVM to process transactions: executing the transaction itself and update the storage. So this plot shows the average transaction processing time. The x-axis shows the block numbers with the major hard forks. And we run the benchmark from the very first block to the 12 millionth block, which is about 3 months ago. And let's first look at the solid lines. The y-axis on the left are for the solid lines, and the solid red and blue line shows the average time spent on transaction execution and the storage update per each transaction. Oops. And there are two spikes on around the 2.5 millionth block. That was the time the Ethereum was under attack. Ethereum soon rolled out 2 hard forks to resolve that attack, including increasing the gas price of the IO-heavy instructions. And despite the spikes, both instruction emulation cost and the storage cost are increasing over time. In total, the average transaction processing time are more than 1.1 milliseconds now. It means the throughput of EVM is about 900. And the y-axis on the right is for the dotted lines. The dotted or the dashed line in this. The dashed line shows the normalized runtime for the transaction execution and the storage update. The storage update takes about 70 to 80% of the total time in transaction processing, where the transaction execution takes about the other 20 to 30%. It seems the storage has taken the majority of the runtime. So let's look at the storage design first. The EVM storage is meaningful storing states. The word state is a map between addresses and to the account states. If the account is a contract account, it has its own private contract storage, which is another a key value map. The state is stored in a Merkle tree structure. It uses hash address as the key and puts the corresponding values on the leaf node. And if it is a contract account, the leaf node has a hash key to retrieve the root node of a contract storage subtree. To the EVM, the storage provides a similar interface compared to a normal key value store. In addition to the get, update, and delete functions, it provides a Merkle proof function. And that is the reason why it needs a Merkle tree layer between the storage interface and the persistent key value store. And this graph shows the runtime breakdown for the storage. It has the same X and Y axis as the previous one. The red line still shows the transaction execution. And the green line here shows the runtime for maintaining the Merkle tree. And the black line shows the database write back at the end of processing each block. While database write back always takes about 0.1 millisecond per transaction, the runtime for the transaction execution and the Merkle tree maintenance are increasing over time. Especially in the past 1 million blocks or so, the Merkle tree maintenance takes about 0.1 milliseconds. That's about 60% of the total transaction processing time. So why the Merkle tree is so slow? Let's look back to a previous slide. When the EVM needs to get a value of a given key, if that is not previously cached, it needs to go to the Merkle tree, and it needs multiple jumps from the state tree node or the contract tree node to the corresponding leaf node to retrieve that value. And that's just an example for get a key. When you need to update the key value on the tree, it's become more complicated. It needs to update all the internal node on the path of retrieving that value. To calculate the new hash values of the internal node on the path, it needs to get the hash value of all the children nodes of those internal nodes. So there are even more amplifications. And that's for the storage. And let's look at the second most time-consuming part, which is the transaction execution or the EVM instruction emulation. There are 3 types of transactions there: the Ether transfer, contract call, including the ERC20 token operations, and the contract creation. This graph shows the average number of those 3 types of transactions in a block. The contract call surpassed the Ether transfer around 5 million block and became the most popular type of transaction. And with the recent increase in the DeFi apps, and the gap is even larger. Currently, there are about 190 transactions per block, and 115 of them are contract calls, and the 75 are the Ether transfer. And now we'll look at the execution time of different types of transactions in a block. The red line shows the contract call takes about more than 90% of the transaction execution time. And if we zoom in further and look at the instructions, this graph shows the top 5 most time-consuming instructions. And the most expensive one is the S-load. This is instruction for the EVM to read the value of a given key from the storage. So even it is not the most popular instruction in terms of frequency, but it takes about 30% of the total instruction emulation time. So at the EVM execution, the bottleneck is still the storage. So EVM is probably not the bottleneck of the current Ethereum blockchain, but on one hand, the transactions are becoming more complicated, and people are still trying to explore new possibilities of the smart contract, and the transactions will become more expensive in the future. And on the other hand, with the recent advance in consensus protocol, the Ethereum and the other blockchain systems will need to be able to handle more transactions. But the current EVM design cannot support more than 100 transactions per second. given the current workload. And the bottleneck for the current EVM design is at the authenticated storage. Although it is just at one Merkle proof in addition to the normal key value store, it has huge overhead to maintain it. Therefore, we are doing research to find a better VM design and the storage design for the blockchain. So if you are interested in collaboration or provide funding to our research, please contact me. Thanks.
Thanks very much, Hongbo.